this, so I don't actually have a slide about myself. But I did H2O for 7 years, doing data science about 10 years, Kaggle for about the same. Pretty much right when I started learning it, I started my first Kaggle competition, got hooked on that, and I've been doing all that since. Mostly tabular. And what we're talking about here is deep learning AI. And actually, I probably have as much experience with the AI inside this tool as I do on Kaggle. So it's fun to do those, but I'm not an expert in those as much as the tabular stuff. And so I think, I've been doing this for about 3 years. We did it kind of organically, so I've been working a lot with H2O with PwC, probably about 5, 6 of those 7 years with them, and they brought us a problem that we just dove right in. We did a little bit of research. We didn't see much that we liked out there. There are people doing this that we'll talk about, but we kind of learned it with them. It was a long project, actually. It took us a while to learn what you're going to see in front of you. It was about a year doing it kind of the wrong way until we finally got the deep learning that you're going to see that backs the overall stuff. So I'll talk a little bit about what Document AI is. It's not just our term, it's actually a pretty big market right now. There's a lot of people doing this, a lot of investment in startups, and most of your big cloud players have some offering here. So it's going to get more common, and it's interesting because it's kind of a little boring. So it surprised us that it's such a big deal, but it is. So what you're going to see, I'll talk a little about what is Document AI, what are we trying to do? Some of the use cases that we've seen at H2O, just different kind of documents, and what you can do with those, and some of the follow-on stuff that you can do with that. And then the basics, the topics here. So you're going to see there's 2 main phases of what we're doing, and each one involves deep learning. Some of it is computer vision, so we have images, and that's the OCR phase. And then we have a multimodal, but it's really an NLP model plus a little bit of extra stuff. So we'll talk about that. And a little bit about how we're doing Document AI, how we wire this together. And then some of the topics that are interesting to me, especially coming from the tabular world and H2O, we dealt with a lot of different clients. And in the tabular world, there's just a difference in how you get your data that I think the deep learning thing that I've become accustomed to. There's a lot of annotation. A lot of people don't have data annotated, so I'll talk about that a little bit, and that's part of our product there. But I'm just kind of curious to see as deep learning gets more and more common. Like, it's been out there for a long time. There's a lot of cool stuff people are already doing with it, but I think it's just it's a different ballgame when you're trying to do how you think about the problems. There's feature engineering, things like that. It's almost like a night and day kind of approach. It feels like to me from the tabular side, doing most of my data science in the tabular side. And then a little bit with specific to Document AI, the AI approaches and some things that like lessons learned essentially and what makes a difference. Again, these are very different from like your tabular world. One of them's kind of the same, but there's a lot of different stuff here. So let's get started a little bit. I'll try and flash back and forth between the product and show you some of the stuff in there and just demonstrate what it kind of looks like to do some of these. But start out with the high level kind of thing. This is ours specifically. It's similar to others. So H2O Document AI, the overview, real basic. We're going to get documents in on the left. We're going to process it with everything we're going to talk about tonight. And then this is so what do you do there? So there's a few different components of how we're doing this. Again, like I kind of previewed a little bit, the labeling, validation, refinement. And that's not normal for tabular data sets. What are we doing? Entity extraction, page classification. So there's 2 main tasks that H2O handles here. So you bring in a document, and what are we trying to do with it? I'm going to do it in reverse order here. So the basic one is to get something like a PDF, or it could be an image. And with a PDF, one of our first use cases here for H2O, after we did some of the PwC work, was to look at every page in that PDF and decide what is it. Look at the entire page and decide what is that page. Because this was a medical referral, but it wasn't just a referral document. So this is one physician group referring a person into another physician group, and they all use different forms when they're doing it. But they don't just use the forms of all the information about the referral. They also put a fast cover page on it, some clinical notes, all sorts of other things that are not just the core form of the referral. So the first thing we wanted to do was to figure out what all the pages were, where's the referral, and there's about 15 different things that customer was looking at. And it turns out it's pretty common. The use cases we have, half of them have this kind of thing. Looking at the page overall and saying, what is this? And some of them route it on a different way. Some of them just want to know something, yielding a flag or something like that. Backwards, the entity extraction is what 100% of people are trying to do. And so this is looking at a document and trying to figure out something. You can think of this as like name entity recognition. A lot of different like text, like token classification, all the different kind of words of what we're doing here. And we'll definitely show this, we'll get this point across for sure. But we're going to look at all the text on a document, and what we're trying to do is classify everything according to what every different customer wants. And that's H2O Document AI. So Document AI overall, the landscape, I meant to put a slide on here, but I don't have one. People are doing this differently. So I'm going to talk about a pretty cool model we're going to be using here, and it's good that we do, so I think we're going to use one of the fanciest ways of classifying these. We're using a custom model to do it, this multimodal model, so we'll definitely get into that. When you look at what some other people are doing, Document AI is not a really defined space as far as what you see on this screen here, so that entity extraction, page classification, people may do that, but some don't. Like if you go to Google right now and you do Document AI, what they're going to do is they're going to have models that understand documents and try to deliver sight unseen. They just have models for you, and you dump a document in, and they're going to do key value matching. They're going to give you their best shot at tables, extraction, something they don't need to know your document. So these referrals, they'll try to figure out when it says first name and Mark and last name Landry, they'll try to associate those keys and values, and that's what it is. So they have the best model possible to do that, hopefully. I don't know, we don't check, but we're doing something different where we're going to customize everything. Because the second you try to say that referral date is today, they can't quite do that. Especially if it's, it depends. They can do that if it says referral date. But a lot of times, a lot of these forms are not self-descriptive. It's not all about keys and values and tables and things like that. And some of the tables are tricky. So other people, one different thing that Document AI really is so that's generic Document AI, what I would say, is it's a single pre-trained model. It tends to be that is there to do a specific purpose no matter what document you bring in. And so that's the other side of where the Document AI kind of landscape goes is templates. And so you're going to get the same document over and over again, or maybe a small selection. This is where your robotic process automation people will exist, and there's some others. Microsoft has a really popular form recognizer tool. It's a really popular marketing pitch. Bring 5 documents in and we'll get a model for you. Because it's really similar every single time. So you're going to see the same one all the time, and they're going to learn the model with minimal training. So you bring 5 in, you label those in a way that you'll see it, and it's similar to what we're doing here, and they'll get a model for you. And we can do that too, but what we're focusing on with our specific way into this marketplace is to do custom entity extraction. So we'll see how that matters a little bit. And integrations, what this does, so we've got documents on the left, the whole tool on the right, but you're going to get a JSON out at the end, and you're going to do something with it. And so I'll show that in the use case in a little bit. That right side is a key element of what you got to be thinking about when you think about use cases for this. And this is not unlike many other use cases, and just everything in data science really. What's the end output of what I'm trying to do? Sometimes it's directly just send it on its way. It's a credit score. Even that, you're going to send it into some database, and then they're going to go use it in the front end or something like that, or make decisions on it. Here, the human in the loop is kind of a big deal for review and correction. There's a few ways you can use that to your advantage, but a lot of processes in Document AI is kind of a boring topic, and there's a lot of people doing these manually. And so kind of the goal that we've seen is to minimize the human in the loop as much as possible, but then get them to train the models to be better and better. So this is that medical referral I was talking about. This is a simplified version of it. Well, we deep learning even for me, so we're doing classification, we're doing multinomial classification, so a lot of different things we're going to find in this form. You see a few examples of that: date of birth, the name, looks like referral date, referral reason, referral link on the right side. The actual use case had 100, when they brought it to us, had like 220, something like that. We collapsed things that were duplicates, just different ways of saying the same thing, and got about 116 things. And coming from a tabular world, if you will run your GBM, your light GBM XGBoost model on a multinomial problem with 116 classes, you're going to wait a long time because they handle that one by one by one by one. That's just how those models work. Nearly all of our models do that, all the tree models for sure. But deep learning is a whole different thing, and it's efficient about this. It handles that in no time. And so I'm still uncomfortable. Like, are we really going to throw all that through there? And it was fine. So that's an interesting one for me. It's not dissimilar from anything else. There's nothing about Document AI that makes that different. It's just a really big advantage of deep learning. We've known that at H2O for a long time. We've got H2O3, our product, our open source product, has had CPU-based deep learning, just really efficient way of doing that. And we know we were out on ML. Like once we saw a lot of classes, we should really think first of trying to deep learning because we don't have to run 16 models to model 16 classes that way. So that's kind of interesting. So here's a medical referral. This is one form, and as you can probably expect, we're just pulling certain things out of here. So we've got labels of these annotations trying to show what the model's doing. But here there's a date of birth we're pulling out. Usually what customers want to do, they don't really want to see, this is interesting for us labeling too. So a lot of people think you would want to try to, you can't even see it because we covered it up. I'll show this in a couple different ways, but maybe there's a date birth or a birth date right above that. What we're always going for, people don't really want to see the context of it. What we're going to do is let the model learn the context. Because, like I said, we're usually using all different forms. So UCSF had template processing here, and they had trained 100 different versions of this. So there's just different physician groups in the US passing these documents around. They got their 100 most common templatized, essentially, with an RPA vendor, but that was still only about 60% of the volume. So for 40%, they're left with nothing. And so that's why it sort of came to us trying to explore Document AI, because what we can, with doing it a different way, we're training a generalized model that understands what they're going after. So this form will change to other, oops, yeah, I'm showing my notes here somewhere. So here's just a different referral form, and I'll show a bunch of these when I get into the demo. But this is a referral form, and here's a different referral form. We can change these forms all we want. Similar content, referred to in different ways. We don't have to go keyword searching. And so that's here. One big difference if you're going to use, for example, a lot of people have experience with Amazon's like Textract. And a lot of people just think it's OCR. So I'm going to get OCR out, and I'm going to write some custom post-processing to go figure out date of birth. And so I'm going to look for a few ways that we might see date of birth, or maybe I'll use an NLP model with some features like a Spacey or something like that to try to capture these. But Spacey will generally tell you that that's the date. It won't necessarily tell you the date of birth, especially if it's sparse and it's not very clear of what these are. This form's pretty clear about what it's saying. One other difference with forms rather than like NLP models to try to do so trying to go just OCR, the OCR is just going to digitize this text and send it on its way. And then you have a pilot text, and what are you going to do with that? So you can run a BERT model. It's an AI meetup, so hopefully you guys know, BERT is sort of the more or less baseline state-of-the-art model these days. And our algorithm uses that as a baseline as well. We have several different models of the chain, Roberta, DBERTA, FinBERT. There's all sorts of cool BERT variants that are out there. You find it specific to context, so it's a pretty reasonable thing to do, but these forms are a little different. It doesn't read left to right, top down. This one, the clues are often, sometimes it'll be above it, and so if you're reading left to right, you're going to see all the headers, and then you're going to see all the text. And how you associate one from the other is not clear. Now, the BERT models are pretty smart. They can actually figure some of these out, but we're going to go for a model that's going to do a little more than that. So we'll get there. So these are some of the use cases we've run into so far. I think, being a product, a software company, we're typically dealing with clients who are asking us, hey, have you done this? Have you done this? Will it work for this? Will it work for this? My kind of data scientist, I guess, the one I am, just figures out the document's the document. Let's look at it. It's not industry specific. It's not document specific. But everyone wants to see their use cases. So, and I think what's interesting, again, I've said this a couple times, that we're trying to expand on that too much, but when we got our first one of these from audit firm over here, who's BBC, who's bank confirmation listed third, that was the first thing that came through. That's an auditor. So, and they're going to get a document. Pretty much the client says they have $1 million in their books. Auditors are legislated to be very regulated to be allowed to go ask the bank, we have this common client, can you tell me how much they have in their bank account? And that document needs to be sent straight to the auditor and not interfered with, and they're going to say they have $1 million. Okay, cool, we're happy with that. So BBC has to do this. It's really boring. Most of the time things match. But they still have to process these. It's an important part of the audit to just make sure it's third-party evidence that says that. But every bank has their own template for it. Many banks have 5 or 6 different templates for it. So we, like many people, in fact, it was knowing we wanted a better model, we sort of fake it till you make it sort of approach at first, and we templatized these as well. I wrote about 30 templates in R myself. They weren't great, but they did the job to just see whether the product was worthwhile. So we started there, but when we looked, it's just unbelievably hard sometimes to figure out little nuances in these documents. You would see people, they refer to it almost with no evidence. Like, we would have a table, currency is one of the things we had to pull out. And you have all these balances, and the currency would have been the table header, and it said British pounds unless otherwise specified. So everything that didn't have any text around it, you had to know was British pounds. That's difficult, trying to figure out how you go through an approach that will figure out that kind of context, that I need to take something from the header and bring it down every single line that's missing something. And yet we now have models that can actually handle that kind of stuff. That's a tough one for it, but we got that to work. Looking at these use cases though, so there's just a lot of different forms you can have, and they are kind of boring. That's why PwC came to us. They had people doing this. Most of these things up on the screen, there are people doing this by hand. And they're good at it. We're all pretty good at this. Most of these use cases, you can be trained to do it in about 15 or 30 minutes maybe. A few of them are a little harder, but it's boring stuff. And so what we're kind of doing with Document AI didn't feel that exciting, but I've actually gotten very passionate about it. But what's interesting is there's a lot of, because putting humans to this task is very expensive and it's very boring for the people. So a lot of these, it's not necessarily like workforce replacement, it's just freeing them up to do better things. But there's a lot of people paying a lot of money to these use cases in every which way. They're going to try to get kind of far away, far along the road rather, with some NLP that they can figure out. We find a lot of people who have become familiar with off-the-shelf tester app, like an OCR tool, and then they tried some other things with using some of the other cloud vendors, like a text or something, to get them as close as they can, and then it isn't good enough. Because something interesting about the Document AI use case is that, and this is going to be the case for some other things too, but we're trying to help people go faster, mostly. And like I said earlier, there's that human in the loop. We're not perfect either. Not one of these models will we ever say is 100%. Somebody's gotten very close. That bank confirmation one, we registered about 95% all the way to the end. But still, it's 5% error, so what do you do about that? So we're trying to get the human load down. So humans are still involved to correct those 5% mistakes. What the best we can usually do is point them to where we know there's a mistake, or there's a likely mistake. So getting probabilities in here is important. These solutions, you really have to think about the end of what's going to happen with these, and how do I work that out? And then essentially, what's my bar for ROI? Where do I go positive for ROI? I've got 4 people doing this today. Can we get that down to 2? Like, that's enough. That's enough to have spent the time to do this, because then you get to save that forever. That's usually what these are. These documents will keep coming in. And so setting up a model to handle this, we're generally trying to find that ROI where we save people more time. And so if someone has to go check our work and we're wrong half of the time, it's usually way slower for them to check than it is to just do it themselves. You can alt tab real fast. There's a PDF and go type some stuff in. So this gets them started, and in many of these cases, so I've got this broken out. You can see there's quite a lot of the ones we've done are in this validation group. And validation means I've got 2 sources. Like I talked about the bank confirmation. We're going to get a document that says that my company has $4.2 million in Canadian dollars. Then we also have a secondary source that we can check with. And those are really nice, because then if you make mistakes, you've got that alternating factor. You know you've made a mistake. You can highlight them, and so you can see that actually over half the ones we have are like that validation and partial validation, where we have a kind of clue. And this is good for ROI. I mean, you want to do this all the time. You want to try to issue these predictions, but when you have that comfort to know that I can check this against there, and if it's wrong, I can highlight it to people, then you take advantage of that. So we've got user interfaces that will highlight that in red and show somebody, hey, it says Mark Landry over here, and it says Craig Landry over here. Like, that's not the same. Go check that out. In that case, we'd be right, and then we check it out too. And I said they're most often correct. They're actually not really. The balances are often off by a little bit, and so most of the things people are checking were legitimate issues. They're not fraud going on most of the time. It was just a daily balance or something like that. But we were able to flag things for people, and that's the whole reason of doing the process. We don't want to just make a rubber stamp. We're actually trying to validate what we're doing here to make this useful. Partial publishing, but digitization is probably what everyone thinks of first, like that healthcare one. We didn't have a source. We're trying to read that referral. We don't know what's on it at all. And so we're just trying to digitize as much as we can. And again, we know we're not perfect, so there's a human that logs in there and looks at everything. We just need to speed up their process. And there's a lot of metrics of how much time they're saving. That's important with these processes. So it may be boring, but there's big opportunity here. There's lots of people, and like every business, it's weird to think that we're still shipping around physical documents right now, but we are. People are businesses to business documents. They're not going away just yet. Judgment, the very last one. That's one of the coolest ones we have. I would scare a little bit, but there's a bank was looking to do something, and when we were presented a problem, we were trying to find a particular fee structure that they had, but they wanted to go ahead and said, well, there's some interesting ones and there's some less interesting ones, and so we want to figure that out right away. That's what we're trying to do here. And I cautioned them up front. I said, well, let's do what Document AI does first and just do the name entity extraction and the recognition, the token extraction. Let's get those fees out, and then let's see if we need a downstream model, thinking I might need something bigger, a real custom, like NLP model. But I haven't talked about too much here, but I said a little bit about it. But we're using a BERT variant. It's a very strong model that we're using here. And so actually, they just went for it all at once. And it worked really well. It was, they were surprised at how well it worked. That one's in the upper 90s on both precision and recall. And I almost cautioned them against trying to do that. So what's happening here again is we're not just getting, you can think of what you're, reading a bank statement, what those transactions are. They were taking the context of what's in those transactions, more or less, and trying to decide whether what they wanted to do was good or was interesting or not interesting. And it was able to do that. So it was not just finding the text, it was actually going ahead and taking that a whole different level that was actually kind of hard to do. So that was exciting. All right. This was a little bit of showing the kind of the process that we go through again. I talked about it a little bit, where we're just trying to show the model. So I'm going to skip ahead a little bit to get into the actual stuff. Other document types, those use cases already kind of segue. So we start with those referrals, but this can handle almost anything. We've got receipts on the right. We've got some checks in the middle. Those are tough. But getting there with trying to be able to read handwriting. This is what a lot of clients ask. A lot of people working the OCR stuff are some have clean digital documents where you don't even have to use OCR at all, and some have really difficult documents, and these are kind of in between. Difficult is also blurry, not just blurry. We can handle blurry pretty well because we're using good computer vision models. Talk about it a bit, but just poor quality. It's been crumpled up, and someone took a camera phone picture of it, and it's really hard to read for a human. So, but always on the table, trying to process all of this kind of stuff. We just mainly need to extract those characters and set a language model plus on top of that and figure out what we can do with that. So, this is the point where I'm going to go ahead and show what we're doing here. Alright, so let's take a look at H2O's solution. Okay, so this is Document AI, the product. How that looks. Could be the same result here. Okay, so we have a bunch of products in here. I thought it'd be kind of fun to throw the models, documentation about the models we use inside here and actually start OCR on those just for the fun of it. So I've loaded a few of those. One big part of it, so when you start with a document set, it's very, create a project, someone's going to want to throw some documents in. You thought about it, you just want to try it, you got a handful of these things, and the first thing to do is just kind of look at the documents. This is a very visual process, these documents. We all, as humans, are good at figuring out what we're going to do. In fact, this one's not good enough just yet. Let me show you these guys. Okay, so I've loaded, these are medical lab tests. Just found from the internet. Some client gave us these a while back, actually. It's been an interesting data set for us to use, but they zoom right. So lab test results. So someone's gone and gotten a whole panel of lab test results. Typical stuff we have header and detail type stuff. So we've got things that are going to repeat about once per page. And that's an interesting part about Document AI. Sometimes the information repeats on every single page, so you get duplicates essentially. And then the main part of what we're doing here is trying to look at the test results. And so here's our tool. So again, it's a very visual process. Like, what are we trying to do? So if I'm processing these lab test results, I'm going to look through a few of these. And I did this one. Connection. Good. Look through these different formats. So here we go. This is the difference. This is one from vendor LabCorp. Here we're going for ThyroCare. I think another LabCorp, kind of popular, but all different formats, right? Every time I flip through these, you can see. And it's mostly, though, you can see, because I've labeled these, I'll talk about that in a sec, but I've labeled what we're going after, the actual meat of the lab test result. Now, this is what we're trying to see. All the different test values that were returned. But even that, as it's mostly tabular for most of these. But then we get this guy. So this one's interesting. And it took me a while to figure out what we're even looking at here. So it's not even the same, but the model's able to learn some of these. I'll show you that in a sec too. So we've got a collection of mixed documents. That's what we're looking at here. The theme is the same. They're all medical lab test results. These presumably would be sent into a healthcare system or something like that, coming from wherever their people are getting the lab test results. And somebody wanted to process those. While I was in and out. So I picked a few kind of trivial things here. So we have patient last name, first name, we've got a test date. But the main thing we're trying to do here is grab all of these values. And so line test description, line test value, on the bottom right, line test interval, what they're doing here. And so the start is, what are we going after here? And so what we've got, we've got an interactive labeler, a little bit of them, so we're looking at the documents. The first thing you're generally going to do is look, what do I want to do? Now sometimes someone's going to tell you what they want to do, but even that's not clear. So a lot of times we'll go from the list, like, okay, this is the 17 things we want out of here. And how do you set your project up? It's actually pretty fast. So we're just doing classification. So from scratch, I type these in, but it would take me about a minute to type these values in. So that'll go label my project. So I've looked at a few of these, thought about how I want to set my project up, what are my classes, whether I know or I'm creating these on the fly. A lot of times I'm doing this just to get ready for something, so I'm doing these myself. What would we want out of these documents? And then how do you get started? So the first use case I said was that they have been doing templates. They have been doing 100 templates. They had hundreds of thousands of pages of labeled data when they came to us. That was fortunate. Most people don't. Most people have tried these, and even if they know the answers because they've done it in the past, somebody filled out a form, most clients can't even actually pin the answers they have in a database to the documents themselves. So you're kind of starting from scratch very often, and some people either haven't tried these or just can't get they can't get at the results. So we've got an interactive labeler that will let them create their training data. And the cycle that we want to do is have this be iterative. Annotating data can be expensive. It can take a while. I've gotten pretty good at it. I've done more than my fair share of labeling. At PwC, we had a bunch of data scientists labeling the data. Eventually, after about a year and a half, we managed to effectively in-house outsource that and get some other people to do that. But for a while, it was us doing it all the time, and we just split up the labeling jobs. And it's not terribly fun work. Although, to be honest, for the first hour or two of every single project, I feel like I learned something about it. Because when you're sitting there trying to figure out how to teach the model what the answers are, and from scratch, you see some of these hiccups. Some of the difficult cases will show up that later, when you've got the models coming in, you'll start to recognize later, like, oh, how do I handle this situation? I can barely tell. What does this mean? Things like that. When you're forced to actually create the labels, there's something good that comes out of that. But after about an hour or two, it's probably enough. So what we try to encourage people to do is start small. Start with something like 50 documents or whatever you can do in a few hours or so. It's useful to get a little bit of volume, but you don't need all that much to get it going, because the model we're going to use has been pre-trained on 11 million documents. So let me switch to that real quick. So we're going to use a LLM model. Loaded that in here. It's be fun. try to get links in the Meetup somehow. So this is the main model that we use. This is a model that is designed to handle documents. So layout LM, the LM stands for language model. So it's really fusing together the language model and the layout of the documents. Like I talked about, trying to parse the tables, trying to do other things that are not in reading order. That's usually what I think of. Why are we using this? Because documents typically come to us and they're not in reading order, top, down, left, right, in this, not all languages. But the model that's trained is, our BERT models are expecting that. They're expecting things to be next to each other. Using context, they can see a lot of tokens at one time, and this one can too. The default BERT model will have about 512 BERT tokens. Tokens here are space-delimited words, and that's going to be the same as you would do in a normal text with NLP. And that buffer is really interesting to think about because we run over it a lot. And so how do you handle that? So essentially, on average, we usually have about 2 passes through a document to get through one because we can only fit 510 BERT tokens. But BERT tokens, for those of you that ever mess with them, they create more tokens. So we usually only get about 300 tokens or so, sometimes 400, some less. But tokens of what we would think is natural language, the way we're just reading these, in as BERT tokens. And then we fill up our buffer. So what we're going to do at that point, we're going to run this, we're going to send all of those tokens into the model and ask it to classify either of our tasks. There's a special way we can set up the way to do the page classification so it has one target. But the more common one, like I said, is to classify every single token. And it does that all in one shot. So every one of those tokens is going to classify and then send those all back to us. And for each one of those, it's going to use the context of the whole thing to figure it out. And that's, BERT is really just, it's a bi-directional thing. That's worth studying if you don't know what that is. BERT's been around for 3-ish years, maybe more by now. Probably so. But it improves where we're going from what we've been doing in NLP, mostly because the way they train it actually is to get a whole bunch of text and it's trained on itself. It's not trained to do any task you necessarily ordinarily want to do. It just winds up this powerful language model where they're going to roll the dice and hide about, I think, once out of every 5th token or so, and have to use all the context there to predict the one that's hidden. So it's training, like, hide a word and see if it can use all the context to predict what that word is. That's the general idea of how it works. So Layout LM, this is a paper by Microsoft Research, actually, out of in Asia. There's a couple of Chinese universities as well. They came along and, let me show you what, this is what our network looks like. I haven't talked too much about it, but, oops. So the entirety of BERT is going to be this text embedding right here. And then we're going to throw in position embeddings. And so that's the layout part of this. So if we looked at the NLP tokens, in fact, so I have run this through, this is going through the OCR. I'll go back and talk about that a little bit. I didn't quite need to step over that, but I have. So we're already in the language portion of this. All these boxes are important. And this is pretty trivial. Almost all OCR systems will deliver these if you know how to use it correctly. They're going to, as they go through this, because what the OCR systems are actually going to do, there's a 2-phase approach here. So the 2-phase approach, the first thing they do is they're going to look at the image of what you give it. So this is a computer vision. So when we take a PDF, we turn it into an image, and then we send the image into the OCR system. And the OCR system's first job is to do segmentation, detection. So it's going to look at that overall image and find all the little parts of interest in there, regions of interest. So for computer vision models, it's a pretty classic thing. Like self-driving cars, when it goes and looks at a view, it's no longer just trying to do one image like we were 15 years ago, like dog, cat, mouse, a chair, things like that. We're now trying to use these models to find multiple objects inside all these pictures. OCR is the same way. We've got a whole bunch of things on this page, and we want our OCR system to find them. But we've seen it's got to avoid the things that aren't words and try to predict things that aren't words. And it marks, there's some of these lines that we don't want it to go after, and just find the text. So its first job is to pass through this document, find all of the existence of these tokens that it thinks we want. And it's been pre-trained to do that. And then, one by one, it's going to send each of those regions of interest to a recognition model. And that's where the language portion of this comes in. Character detection. This isn't really a word. Let's see how it did it. It didn't do so hot, I missed one of these here. So the math formulas are interesting to us as we're trying to study some things in documents. But so that's the basic idea of the OCR systems, is that not all of them, like Tesseract is a common off-the-shelf one that we include in here if you want to use it. It's just kind of altogether different. But the computer vision systems typically have that two-pass system. So they're going to first find all the text one by one, send that into a recognition model. So you're kind of actively maintaining both models. And so we're working on improving ours. In our system, we've got a model called DocTR. I've got a few links over here to that. Which is that two-level system. And we noticed that we used the default models that they had, and this is interesting for the computer vision part too. So passing around a bit, but with the OCR system, that detection model would often miss some of these boxes, and still does, because we have changes coming into this really quick. I think I caught some that weren't. See right here, it's missed this entire row. And what we tried to do, so product-wise, we took a model where the benchmarks are really good. I have them up somewhere around here. Really good when you compare it to Google. They compared it to Google and Amazon, and we've since compared it to Azure as well. But it does right in there with those. Whereas when you look at Tesseract or something kind of a little worse, Tesseract is pretty good at clean documents like this one. But when it got dirty at all, it goes blind for certain things. It's not a computer vision model the same way, so it's not robust in the computer vision side. But the interesting thing about the computer vision models here for us, we had a TensorFlow segmentation model, so the one finding all the tokens, and then we had a PyTorch recognition model. And everything else in our stack was PyTorch. So we got rid of the TensorFlow model so that we could have a lighter load on the engineering side. It took us a little while. We didn't have strong enough regression tests to show us when we did that, the pre-trained models. So the DocTR that we went to, the pre-trained models we had both. We had one for PyTorch, we had one for TensorFlow. So all we had to do was swap them out and move along. And so the engineering part of that was easy. What we realized for a couple months was the TensorFlow model was better than the PyTorch model, just the pre-trained one. We don't really know why. It should have been the same data sets going in. And but there's two answers why. And so we've since figured out that the engineering behind it, they were doing padding on some of this, and there's just mistakes. And so it took us a while. There's 3 other Kaggle Grandmasters on my team, so we have a stacked team, and yet still it took us quite a while to figure this out. So it's interesting with the two. Those are our dominant deep learning frameworks out here. They're mainly meant to be interchangeable. It's up to all of you to figure out what are the pros and cons of using each different library. Standardization is nice. We don't have to bring in as many things. These are big loads to get some of these things in. But it's not always the same if you're using pre-training stuff, so sorry. But so we do notice that it's missing some of these. The other one, and we started pre-training some of this ourselves. So getting back to what the LLM portion is doing, so that's why we have all of these boxes here too. So the big difference, so there's text embeddings, everything's embedding to position embeddings. The embedding space looks kind of strange if you look at it. What we're doing here, these position embeddings that they're using are going to take the pixel locations and put them in a 0 to 1,000 scale, and then run that through an embedding layer. And normally, okay, it's a function, and let's move it over, and someone decided to profile it, and it's just interesting in that it wasn't like this straight line that goes from 0 to 1,000. We would think that that's what it is, but I guess maybe that the authors decided that the top of things and the left of things was where most of the action was, but the embedding layer goes up sharply and then moves over to the right. Nothing to that. It was just kind of interesting that you would think the embedding space is pretty simple. Let's just get 0 to 1,000 into a deep learning scale that fits it better. But all these little things are just sometimes intriguing when you got to peer under the hood and look at it. So position embeddings are going to take the box location so it can see where it is on the page, and it's going to see how big it is as well, how wide, how big a word it is, and also how tall, how big the font is. You can infer all that stuff from here. Whether it does or not, the model knows. it's so tough to tell what's useful, but definitely the alignment of all these things is really what it's allowed to do. You can see right justification that way, you can see top, bottom, left justification, all of that. And we see that be powerful. It was one of the biggest things. So before we used this model, we were trying to do every single token by itself and send in features of what was next to it. We tried to put all sorts of different features in there next to this model, and we used some really good encoding schemes, really good NLP schemes actually in there. But we couldn't be consistent about things that wavered because they just didn't have that positional encoding part of this. So trying to hand roll our own, it was just like one of these moments. I know where I was when I saw this thing finally look smart. It was like, wow, this is AI finally. Because we would have a table of these bank confirmations, and people would have a balance and interest. And balance and interest are both numbers, and they were both next to the accounts. And if I couldn't send the features of the table headers, it was very difficult. And if the big ones were more likely to be balanced, the small ones were not, but then you have all zeros. And what we would be showing our users is we'd be haphazardly picking from the two columns, and we'd be wrong about most of them. Sometimes you even get the right number. That's interesting with the validation case. 0 is the balance, 0 is the interest. But you've got humans involved, and they don't want you to be right for the wrong reasons. You shouldn't be right for the wrong reasons, to be honest. So, but it was so frustrating to us. And then when we put this model in, that was the first moment I started to see this thing is almost always right. Not always, but it was so consistent. Like you could really see how this whole thing came alive. Like it finally started to see the layout matter for these documents. So it got all the language stuff. We didn't have to do anything. I mean, this model is just shove your data in, get your answers out. It's simple. It's not like rows and columns. You're not trying to think of even how you would include the embeddings. We're not throwing different vectors in there with other features. For better or worse. So for better is that this is simple. As long as you can hook it up on the engineering side, you can use it, and it's really powerful. This is transfer learning. It's been trained on 11 million documents. It took them a whole bunch of GPUs and weeks to train this thing, and who knows how many other failed experiments came before it. This thing is strong. We use the same pre-trained model every single time. It's really powerful. And it just gets you going quickly. And so with that medical lab test results, let me flip back to that real quick. Show you what that looks like. Starting quickly is really important because again, we're trying to connect this whole workflow. A lot of people don't have anything to start with. So if they're going to sit there and label things and click on boxes, we want them to do that as little as possible. Let's get a model in there that can learn that and make some mistakes and then just have them correct that. That's the cycle we want to see. Is put as minimal human effort as you can into training this thing, and then figure out where that inflection point is, where the model's close enough that you were faster to correct it than you were to create from scratch. And sometimes different use cases mean that means in different ways. If you only have a few boxes, that's usually pretty quick. If you have a lot of stuff on there, it can be a bit harder for the model to be precise enough because you got to check a lot of stuff. Here we go. This is in sample predictions. So this is what the model's learned at a sample. It's a little lower, but not sure I was reading like this. Okay, so we're doing classification here. So what I've done, this is the important thing. I've got 11 documents, and I've got 20 pages, and these are the ones we're looking at earlier, the lab test results. So I've got a big table in there, and some header stuff I picked out. And it's classification, so we're looking at things in a pretty typical way. So we've got our F1 score, our precision, our recall, support, and here is the number of tokens in that class. So that's essentially our volume by counting by tokens rather than documents or pages or anything like that. This one's interesting because the very first thing you see is the macro average, 53, not that great. The micro average is 97, and it's very different, and we'll see why. So there's 3 things you're going to see. These are the things that we paid attention to when we were doing it all on our own, writing all of our own Python scripts to generate everything and do everything without the power of a tool. We were looking at these same kind of things. So here we can see what the story is. So I set up I set up something with how many classes, 10-ish classes or so. And here we can see the F1 facility name. That's going to be something that pops up one time a document. I think of these always as header and detail kind of stuff where you repeat one-to-end relationships. I've got facility name, I've generally got 1 per page, 1 per document maybe, 1 per page. Line test description was part of that big table down there with a lot of tokens. And so we learned that really well. So 9959 F1, we have really high precision, full recall. We didn't miss a single one. This is training data, but if we went down a little lower, we'll see that it's still pretty admirable even at 11 documents. We can actually really start to learn some things that generalize at a sample. So we see clearly this support over here in the right is what's going on. So this model's managed to learn things already. And if we look at it, it's already trying to learn that structure top down. It's learned really well. And we can't throw new documents at it. And it already is trying to learn the structure of that document. So it's used the layout and the language portion a little bit, but here I think the layout is really what's helping it. And the language model is going to see the same thing, right? A pile of numbers is not going to be what the test is. A pile of numbers is going to be the value, and it can figure out a few things here. So it's not a hard format necessarily to learn, but this is, we're accustomed to, I've got to see thousands, hundreds of thousands, millions of things in deep learning sometimes, but with transfer learning, it can be really strong. You can get started kind of easily. And so here, already 1120, I'm going to be probably pretty close to where I'm actually already about as efficient getting that model to start for labeling new stuff. I'd probably throw another 30 or 40 in, it's not that hard. But we'll get there pretty quickly where the model's passable in accuracy, and I can get it to get me going already. We also have confusion matrix. We can see where these things go, and it's no surprise that when we're supposed to predict facility name, that should have shown up right here. It's going to the O token. O means other, it's a special class that just means nothing to see here. So that's the nothing token. And in fact, that's important too with how we calculate these confusion matrices, is that we're going to throw all the O's out. Those would dominate everything and you have really high numbers, but we're actually going to just look at the classes we care about usually. You can do whatever you want, but the way we show it is this way. And that's the most telling, see how all the classes average together. But here in the confusion matrix, we can actually see where things are going, when it's wrong, and it just doesn't have enough positive reinforcement yet to find the facility name. It's putting most of its energy so far, no such thing as energy, but it's putting most of it, all the calculus back there. It's helping it find a table because it's finding a really good reward for that. But we know with volume, we see this same kind of tactic balancing. We very often in this space have unbalanced problems. So we have minority classes and majority classes. I mean, there's a balance of all that table stuff versus the header stuff. But with enough documents, you can get through that. And so for the referral case, where some models were training on like single-digit thousands of documents, and other models we were training like tens of thousands, I want to say 70, 80,000. Never memorized those numbers. But we have quite a lot of documents, and yet still some of the classes they picked were just really rare. Like these are medical referrals, and so you would get like your second contact's cell phone number. A lot of phones don't even ask for a second contact. They just ask, okay, who do we have to contact if there's anything wrong here? So the second contact is kind of rare, asking for a cell phone number rather than just a regular phone number. So we would see, like sometimes there's only 5 of them across the entire data set. And this is kind of how you work. So this is, in most of these problems, we're paying attention to these and trying to inspect what should we be doing? Is this correct? Is it important? Do we need to weight these equally? Is it okay that we're going to miss some of these? Like, we don't have any examples. Maybe we should go sample for those. Like, those are all the decisions you want to kind of be making. One big thing with these is that a lot of times it's unbalanced with what type of a template you're seeing. Like we said, in those examples, we saw 2 LabCorps in there and then some other stuff. In the US, you see a ton of LabCorps that are really popular. After a while, you don't need to see the second 1,000th LabCorp. At the expense of, you want to kind of focus on variety. Let's get this model to generalize rather than try to memorize this thing. With the pixels that it has, with that layout information, we do see occasionally we'll gravitate towards starting to memorize some of these things. They've actually done some kind of powerful stuff to us where we were mislabeling something. We skipped a whole bunch of labels. But the model was smart enough to figure out, because we were trying to auto-generate labels in one case. So we took all these templates, backed it out, and stuck in currency or something like that in there. But it turned out we only had it for like 30% of the data. The other 70% we forgot to label it. But the model was in the 90s because it just figured out the pattern of our labeling. It figured out, oh yeah, I got it. When you tell me Citibank or DBS, then you want the currency. If you're going to send me Barclays or Wells Fargo, you don't want the currency. I don't know why, that's up to you. we didn't mean for that to happen. So it was interesting, again, this visual process of us inspecting, and we would notice there was missing currency a lot. It's like, I don't get it. Well, we have really high accuracy currency. So it's a kind of tricky situation when you're trying to, again, what we're doing is we're fighting that labeling problem. We're trying to get a lot of tools in there to get the labels in, so we were trying to cheat, essentially. We had a few templates and we used them for what they were doing, but we were consistent about how we label things. And I would say there's lots of different ways we had when I tried to get the sort of tips and tricks of trying to do one of these things, like the lessons learned that we've had. In this deep learning space, it's not about features. There's not much more I can do for features. It's got all the features it needs. We don't know how to help it. If there's any more we can do, as people think about, can I put like a red or green light in there if I have some other features? Like, maybe so, but we've never really seen things like that, trying to hack it work. So it's not about features, understanding the problem. It's about, for us, it's always been about the labeling consistency and like simple things. We would have like a 7-page document, and some people, when we wanted like the bank name from it, some people, myself included, would pick it on the very first page. Because at the end of the day, when we show people, we just want to show them the bank name once. But the bank name's on every single page. And in fact, it's in three different places on almost all of those pages. There's 21 opportunities to find it, but people want to see just one. So thinking at the end of the day, like I said, you should be thinking at the overall solution, I just need to return it once. But if you think about what we're doing when we train the model that way, if I only labeled the logo of the bank and I skipped the address and the other portions, and furthermore, on page 2, I didn't even label any of those, in page 3 and page 4. This model works page by page. It doesn't see the entire document, so that's a drawback of what we're doing here. And maybe we'll see that at some point that we can string the entire thing together. But right now we can't. And so what that means is this model is going to have to try to contend with inconsistency of labeling. Like, I see that you've gone for the logo sometimes, and the other things you never go for. And if the logo was absent, we might move it to the address or something like that. So we had to just talk as a group, and it's mostly about consistency. How can we be consistent? Because otherwise, how does the model know what we're up to? I mean, like I say, sometimes it can be sneaky about figuring that out, but consistency is a lot. Like we've done many of these use cases. I've labeled these a lot myself, and I mess it up just about every single time. I do something that's a little wrong or inconsistent, or as you learn how you do it, you take a different approach on this document and a different one, and mentally say, oh, that's about the same. But it's amazing how many mistakes you can make in here. So I've had my team catch me a lot of these times. I usually go first. But some of the other things, let me flip back to this a little bit. So we are working with Document AI, I'm talking about here. So reviewing accuracy, I showed that plus page problem what you call F1. Per class balancing, but label consistency we're talking about here. So reviewing, so what strategies we've used and seen are really basic. It's common for almost everything else except for the second portion. So just reviewing the most incorrect predictions and just looking at those. We have probabilities coming out of these. Which ones are the most wrong? And just focusing on those, understanding that. And that's where we've usually found this inconsistency pop in. What's surprising to me is that actually reviewing the training predictions are even more useful. What is the model struggling to learn even when it has the answers? And that's a bigger giveaway that you've done something that doesn't make sense for it because it learns pretty quickly. So just reverse sorting those as far as the error is something that we do very frequently. I haven't talked too much about the post-processing yet, and given the time, we may not talk about too much. But so we've got, so far, talked about 2 phases a little bit. So we've got our OCR phase that's going to digitize all that text. We send all that text into this layout and model, which is going to see about 500 tokens at a time, and do what we want with it. It's going to, page classification, entity extraction. There's some other things you can do with it. You can do form layout. There's a few other tasks that it can do. Those are the 2 that we find customers have, and we know how to do those. We've done some other grouping kind of things. There's some other things you can do. But we're working in a token world. So every single one of those boxes, I'm going to get the model to predict what it is. And let's say I go for something simple but kind of complex, like instead of first name, last name, I'm just going to go for customer name. So Mark is going to get if it's right, prediction, it's going to be labeled customer name. And then Landry is going to be labeled with the same thing, customer name. And almost nobody wants that at the end of the day. Nobody wants to see independent tokens every single time. So we got to kind of put these together. And so we call this kind of rolling the tokens up to entities. So we want to return the entity, Mark Landry, and tell them that's the customer name. and provide probabilities and the location and all sorts of kind of diagnostics people can do so that they can do whatever they want with it. We found it, we know where it is, this is what we want you to know. More complex post-processing would be to convert that table. So we look at the lab test results, and if you notice, I drew this big giant box over the entire lab test name and a giant box over the value and everything. That's the most efficient way to label. I got one box and I've labeled about 100 tokens or something like that. Because we'll merge those in our tool. I know that I'm going to merge that with the OCR boxes and I'm just going to run an IOU kind of model to figure out where they belong. But when the model's done, we've just provided all those tokens. There's no table structure, it doesn't understand columns. Even though the model probably did to some extent, we don't get that kind of how did you do it out of the model. And so we kind of have to back into some of those things. So, but maybe a third to or more of our use cases involve tables. Actually, probably more like 2/3 to be honest. So there's things you can do after that. We've used models to do that. It's a little overkill. It requires a lot of labeling. So again, if we're going to try to use each of these models, we have to label each of these models. Page classification is really easy. Look at the page, pick a label, usually from a list. That one's pretty easy to label. You can go really fast. Doing the normal name identity, the token classification, trying to do this normal job and name identity recognition part, that's a little harder. If we want to use another model to go group everything together, I'm talking about that too much, but that's more labeling we have to do. So you can hear me just say this over and over. This annotation side of things. Like it feels like I know there's definitely unsupervised learning that exists in the tabular world, right? But in the rows and columns world, especially in enterprise data sets, I think it's fair to say most of the time, the data is just there. The problem I did at Dell, we're trying to figure out how many days it will take to ship a box. If someone orders something today, when is it going to arrive what the customer says? We've got years and years of history of how long it took every single package to arrive where it goes. A few little outliers, but we just know the answer. So you have everything. Just collect the features, shove in the model, you're on your way, you've got millions of data, ready to go. Most of the time here, you're starting from scratch. So that's kind of the pain of how do you get people to do this, which is why I think probably Microsoft invites people like, hey, it only takes 5 forms to get it going, but it can only handle forms. And so what we're looking at here, like this medical lab test results, the little thing I put up there, probably what I showed covered like 7 different forms. So you have to independently label 7 different versions and hope that you cover your main providers and things like that. So that's the difference with H2O. Others can do it. That paper comes from Microsoft. You can wire it up if you want. A lot of what separates like the work we're doing is just the edge cases you get with the OCR. Like even embedded text is really simple. Embedded text is if you go get an order, you go buy something, and you get that invoice back or an order. You can just copy and paste it, right? It's just a digitized document, even if it's a PDF or it's you can convert it to one. So if you get one, there's no need to use a computer vision algorithm. But it's funny, you get these edge cases, like some people decide to load up your document with all this little metadata layer with these 0 by 0 pixels that look like they have a whole lot of text in there. And if you don't know to ignore those, some people will go outside the bounds of the PDF. There's all sorts of kind of weird stuff that we just learn as going through the experience of some of these things too. Post-processing, the errors. So post-processing, other kind of different things you can do, like standardizing text is a common one, trying to get dates and money amounts, stuff like that you can do, and just shift things around. Change the shape of the data is maybe what we're doing in the post-processing phase, and that's why it's kind of painful, because at the end of the day, you want to see Mark Landry as a customer name, not Mark customer name, Landry customer name. But the document, the way that I train my model isn't that way. So once I fuse that together and get one entity and have somebody work in that entity world, if you want to try to get your feedback loop, you've changed the shape of your data, and when you go into tables and things like that. So it's tricky how to get these feedback loops in place, actually. So definitely what we learned is these errors accumulate. So the big 3 phases here, the character recognition phase, really, whether it's optical or embedded text, the modeling phase, which can include a few models or one or more models, and the post-processing. Generally, if your OCR is going to miss 5%, it's very tough to reclaim that. The modeling phase may lose another 5%. You're kind of adding them up. Sometimes it feels multiplicative as well. It's not. But and then the post-processing again. So if I'm going to go enforce a table and I missed a couple tokens, I can cram a couple lines together. I could have done everything right. The OCR could be perfect. My model could be perfect, but I didn't catch the fact that someone was bottom aligned on their table and I missed the first few words, and those can be wrong again. So there's like 3 different things, all of which can fail on you. And that's important to say, because definitely we're having a hard time knowing what to do about this one, but the modeling phase always speaks to us in these model metrics. You get diagnostics, you saw them on the screen there. It's very common to measure how well does our model work. But we've got to appreciate that it's a 3-phase process. In our OCR phase, we're not often training, and we don't often actually know what the ground truth is. That's even harder to ground truth the OCR phase. That's every single token, make sure it's correct. We don't do that. We try to use all sorts of methods to get around that, and everyone does that trains OCR models. They try to digitize things and then make them blurry, almost like a CAPTCHA style, of making it difficult so we get dirty documents, but it's very expensive to sit there and go through 200, 300, 400 tokens on every single document as you need to train these things. You got a little noise in there, so that the errors that go through this system, it can be tricky. You can say, oh, my model's up at, we're doing a good job. My model's at F1 of 85, like it's learning, it's doing a pretty good job, but that doesn't mean your end results are going to come through at 85%. And that's not too different from normal things, but I guess I find that this 3-step pipeline is a lot more balanced than I guess in a lot of tabular problems I've worked on, where you might be doing ensembles and things like that, but all your ensemble members have their own accuracy, and usually when you ensemble them, they get better, not worse. Here, these kind of go down on you. They just get worse a little bit. And so one good illustration of why the OCR phase is important too. So again, if we misread my name and we just read MAR, and the model's strong. The model's probably going to get that right. It's still going to figure out that that's customer name. They just tend to do that. They're not that picky about seeing everything be right. That's what's powerful about seeing these kind of models. This has been trained on documents. I plan on showing some of those, but it's a tobacco data set that's become kind of popular to use open source to the legal battle for tobacco companies in the US. And but they're kind of old documents, but they're very difficult. And that's that paper, the LLM paper out there. There's a lot. That's kind of the tone that they take. They want to make mistakes. They use Tesseract off the shelf. They wanted to make OCR errors. So things have been pre-trained with OCR mistakes, and it knows how to recover from those. And so it's very robust to misspellings, things that they assume that people would be working with, and that's true. A lot of times you do. So we've definitely seen that. So even if it sees my name misspelled, or just missing or something, the LLM will probably get it right. So you think you're correct about that, but actually the OCR phase, you lost it. And so at that point, when you eventually deliver your final prediction, it's not correct, even though you classified it right, supposedly. But any one of these pieces goes wrong, tends to be, it doesn't work out at the end of the day for you. So that's a little hard to swallow sometimes, but something we learned. I think I'm going right around that hour. So I'll send some of the links that I've gotten together. So some of the benchmarks we pay attention to, the OCR kind of world is interesting as we're retraining one of these. We're using H2O tools to do computer vision models. That's all about getting the data sets. And what's interesting there, I guess to me, that's not so much true of the LLM side. That LLM side, we see no real reason to retrain that model. Works really well. There are some other versions of it which we take on, but that one works really well. The OCR phase, a lot of the OCR tools have the focus that is almost either too clean or too difficult. And so the OCR models that are out there from computer vision, a lot of what they're trying to do, what our cloud providers are trying to do is get our phones to work really well. So I can take a picture of that and it will read that entire banner, like things out in the wild or what they're going after. And that's still good. That's what the model we're using are designed for that. But our distribution of the documents we get, we're still doing documents. It's not that critical to be able to read things in just on the side of a door frame. So it's helpful that it gets those models to stretch, but what we're trying to think of is to make sure that we have our validation and test sets aligned so that we get the metrics across these data sets so we can measure things that we find most useful to hit the use cases we want. And we get different customers with all sorts of different flavors. Lots of really clean stuff, lots of stuff not as much, but lots of stuff that is difficult in certain ways. So we do want it to be difficult. We don't want that's overly, it's hinged overly on clean stuff. But the way we look at this and some of the data sets that things are trained on, some of those are just not as valuable to us. So that's the value for us take this on and train our own model and really situate that so it works the best for us. So with that, let me close up and turn it over to questions. So we'll send some of the links to some of the tools I talked about in here on the computer vision side and the NLP side as well later on, so you can read more about that.
You mean the microphone? Any questions?
I think you need a mic. You can hear me, right? Oh, okay.
Hello.
Okay. So a question, right? Because a lot of these models use deep learning models. So we have talked about a lot of the accuracy, right? How about the performance side of things? How do you?
Yeah, that's a good question. So Tesseract, kind of off-the-shelf model, just different, more old school tactics. There's deep learning in there, there's LSTM in there, but yeah, that is a trade-off. And in fact, when we're retraining the model right now, I didn't really say it actually, but so what we've done, we are using a DocTR model, which is created by Mindy, a company in France. We did a public fork of it for a few reasons. We got rid of some libraries we can't use, and we cleaned up a little bit of math inside the segmentation that they had. But now that we're retraining our own, when we looked at the segmentation errors, it wound up being kind of a two-stage process. So for one, we corrected kind of the padding that we saw in the PyTorch model that was consistent with TensorFlow. But we also noticed that when we were often looking at very large documents. People take documents at high DPI a lot these days, like super clear, big high-res images, things like that. And we choose to run them at about 300 DPI. Some people even say try 500, 600, but 300 DPI, 200 DPI, when we're converting from so that's dots per inch, I guess, and PDFs. We get these big images, and we notice that the first layer, the input layer, was 1024, and people were just looking at how that gets crunched down to 100 or so, and so we doubled the input layer size. Just someone thought, hey, maybe that's a good idea. We think we're missing stuff because the small text just becomes too small. And Tesseract, of all things, was actually pretty good about getting that small text. So, but exactly what you said. So we measured it, and I said, okay, well, we definitely need to clock what the difference is here. We noticed it was about 20% more, and so yeah, it's hard to say, And also, all the deep learning stuff comes in here. Like, if we can run things in batch, like really hit up the GPU batch size, that's some of the improvements we're trying to do to get the speed. So we're about So we're about 2 pages per second, so about half a second per image, when we can fully batch these out, I believe. If you don't fully batch them out, you really start to pay a penalty there as well. If you go to CPU, you're going to be even slower. So a lot of people will train on GPUs, use GPUs for all of the model training, including using the OCR and batches to get everything ready to go, and then deploy in a CPU pipeline. That's parallelized, Kubernetes, all that kind of good stuff, but it's CPU at the end of the day. And that's okay. So that's what we usually measure things on the CPU side as far as how long things take to score. So that referral model I talked about scores in about 12 seconds or so. So that's not real time, right? But it's, you can argue whether it's near real time or not. We don't yet have a client who is that upset about that runtime. You get a big document, you might have to wait. Like, at some point we'll probably run into somebody who gets a little upset. But so far, the REST API, people have been pretty understanding of that, I guess. And that seems to be similar to what other people in this space are doing. If you can skip the OCR phase and go to embedded text, you can do that at lightning speed. So you can pick up a 1,000-page document in 2 or 3 seconds if you could just read that text in embedded text. But yeah, that's a good point. That's actually one of the bigger reasons why we keep Tesseract in one of the options that people can pick from. So I didn't show it, but when we load a document in, I went just to show them what the document looks like and training things, but there's an OCR phase there. We just hit a button, run OCR. We give a few different options there, and we'll expand those a lot, especially with the new one we have. I'm not sure that we'll create another parameter right away, but it would be nice to give people like that trade-off. And so yeah, speed's important, because you get a 2,000-page document, that 20% extra overhead, it's just 20% overall too, but all of a sudden, 20%, you're talking like a matter of minutes or something like that can matter to people. So, that is definitely a good trade-off. Any of the OCR systems are already going to be kind of what it feels like a little slow. You're gonna feel those a little bit. all the way, we measured the cloud, Azure, Google, and Amazon. There are others doing that too, but those are the ones we pay attention to most. But, yeah, good question. The LALM one seems fine too. It feels like, but that's another thing that we have to think when we put our pipeline together. If we wanted to, like I talked about a little bit, for inferring tables, we have kind of a heuristic approach behind that. When we did use another LALM model, that's another time cost, right? If I want to put more of these things in the chain, I'm going to be paying, every one of these LALM runs is going to cost me time. Another way, like I said, is of handling if one page is split into two different LALM runs. So you've got that 512 token, 510 I think it really is, but BERT token buffer, and a lot of our documents spill over to two. So you can put a hard cut in there. That'll be the most efficient way to do it for time, but it's not the most efficient way for accuracy. You want to have a little bit of a sliding window so you don't accidentally run into a cutoff. So you show everything enough tokens that it can use a full buffer and see a little bit of carryover. But when you put that sliding window in, that's a little more time cost. So yeah, we're thinking about that a lot, for sure. So, but it's something you want to expect with the use cases too. It's almost about that use case. So we did have one person ask us, "Is this real time?" I was like, "No, it's going to take you 12 seconds. What if we put more hardware at it?" No, that's as fast as you're going to get it out. You're going to be okay with that. So you'll see some. Our phones are doing some pretty amazing stuff. It is going to be common. We said these are kind of boring. It's almost surprising sometimes people are shipping documents around these days, but they are. Because our phones are pretty good at taking a picture of that, and I'm sure it'll digitize it for you really quick on hardware, optimize stuff. Mixed precision, that's another one. We haven't really pushed the envelope on trying to do mixed precision. So we can get a little faster, I believe. I think we still have some room to pick up some speed there. Some other efficiencies we're able to do, but yeah, definitely the time cost of these different models is something you're going to feel in there. So.
Okay, thank you.
Sure.
I think I have another question. This is more towards the product side of things, right? So how does the offering of the H2O Document AI work? So is it something like an off-the-shelf product, or you all mainly do customization with your different clients?
Yeah, there's a whole topic there. So like I keep saying, it's difficult. So off the shelf, what we're getting, I had a little marker on there, I didn't call it out at all, but this little tiny SC over here is for supply chain. So as we gather experience, and you'll see this with the other vendors too. In fact, I did them a disservice. So when I say Google will only do generic document AI, most of the vendors, once they get a hold of a data set, they're trying to find ways to let you start from what they learned. And we're the same. So we're getting more and more supply chain use cases, all different parts of the supply chain. Starts from a contract, and you got an order, then you got an order confirmation, then you get an invoice, all these processes that most of us consumers are just kind of quick. You order something and maybe you get an invoice or something, but all those documents are kind of dealing with the same thing. Like I'm buying stuff, I'm buying a bunch of things on one order, and so they all look very similar. There's a lot of commonality in there, and we've seen that. So we've seen that we trained something on a really poor pile of invoices, honestly, and we were able to process purchase orders pretty well, exactly what I was saying, to get that going. So showing the client, hey look, we haven't done anything, we've never seen your data before, but we can use this invoice model, which is trained differently, but there's a lot of commonality over there. And again, when we went to order confirmations and all the other parts of that. So yeah, that's a big part. So pre-trained models, like I said, like the LALM model, that pre-trained model, that's the typical transfer learning. We've got one big model, we're going to use it for a lot of other things, a lot of think of it as fine-tuning. We're kind of starting from scratch, kind of like the starting point here. Yeah, a lot of people, once you learn the document, then you can at least get a starting point. So that's another tactic for trying to get people to not have to create a whole bunch of boxes, is get them a starting place already, and they can just correct the boxes or whatever if it fit to their needs. And we're seeing that a lot. Some of the use cases we see, and you'll see that some of the other vendors, like the cloud providers, usually have an inventory of stuff like tax documents and lending documents. The lending industry has a ton of documents. So yeah, when people get a hold of some kind of data set that they can get that's strong, yeah, the ability to use that directly gets you just one step closer to customizing for your needs. So right now, we're still a little, so we are mostly starting from scratch and custom, but we can leverage anything we can try. We can also, we've been able to use, LALM requires those boxes, but we don't have to use LALM. I didn't focus on like the paper for LALM measures themselves in different topics against BERT and some other things and some other variations, but generally that's its main competition. Sometimes the margins are thin, like just a couple points or so, like there would be like 90 versus 92 or something like that. Meaning like for all this reading order and and tables and all that kind of stuff. Sometimes Bert can still figure out the job, do a good job at some of these things. What that means is that you can go to your normal like Hugging-Face stuff and find someone that's pre-trained something else. And we've seen that once, talking earlier about we got these physician statements and we were able to take a BioBert model that knew diagnoses and was able to tag all the diagnoses on there. It wasn't perfect, but it was a whole lot better than starting from scratch on some of that stuff. So we'll take, these are, I didn't say too much, to LALM, like BERT, it's a transformers architecture. So you can fairly easily swap them in. We don't have it quite easy enough to swap them in just yet. We have to work on that, but we've done it internally. So that's on our roadmap. It's more of a long-term kind of thing. But yeah, all with the same goal of trying to get that annotation load down so that someone can get something maybe pristine out of the box. Like eventually these supply chain ones will probably get good enough that if you want invoices, we'll have an invoicing model for you. So as we encounter more things, we'll get better at that. Competition's doing the same thing. Good question.
Thanks.
Any more questions?